Okay, I think that's right. All right, so for remote students in the uh, course, there's two things for today. One of them is a set of notes about neutralization. So in the materials section, if you click on Unit 9, acid base, and then there's the folder for the week, and down at the bottom, there's one that says Honors Chemistry Neutralization Reaction Notes and Introduction to Neutralization Reactions. And those are things that students got in class today. And they're about acid-base neutralization. So these are like about the acid-base neutralization notes. Okay, so here's some things to know. It turns out that you can take an acid and a base and react them, and that type of reaction is generically called an acid-base reaction, but it's also called neutralization. Because a solution that's neutral is one that has a pH of 7. It's neither an acid nor a base. And the deal with acids and bases is you already know that acids generically have like hydrogen as a cation and then something else as an anion. So maybe it's sulfuric acid, H, H2SO4. This is an acid because it has hydrogen. And maybe we take sulfuric acid and react it with a base. A really common base is sodium hydroxide. And this, oh, hold on. Those are kind of backward. It sort of doesn't matter. But in this diagram, this is the base. So sodium hydroxide is over here. And then maybe we have sulfuric acid, H2SO4 on this side. So the base is this hydroxide as the anion, and the acid has hydrogen as an uh, as a cation. So what makes the base is that you got hydroxide as an anion, and what makes an acid is that you have hydrogen as a cation. Generally, there's a couple exceptions to that. And hydrogen ions and hydroxide anions, those react to make water, H2O. So if you have an acid with hydrogen ions and base with hydroxide ions, and you react them together, you end up making water. So in this solution of the base, there's a whole bunch of these hydroxide anions kind of floating around, and that's what makes the solution a base. In the acid, there's a whole bunch of these hydrogen anions floating around, and that's what makes it an acid. But when you react them together, the hydrogen from the acid and the hydroxide from the base, they combine to just make neutral water. So you just have more water in solution. And now the hydrogen ions that are in excess are gone. The hydroxide ions that are in excess in the base, they're gone. And those ions combine to just make more water. And water has a pH of 7. So in order to make the neutralization take place completely, it's necessary that the quantity of hydrogen ions and the quantity of hydroxide ions are exactly equal. If you've got more hydrogen than hydroxide, then there's still extra hydrogen ions in solution. If you have more hydroxides than hydrogens, there's still some extra hydroxides in solutions. So in the laboratory, if we spill an acid somewhere, the easiest way to clean up an acid spill is to put a bunch of base on it. Fire departments, like they respond to crashes, hazmat groups, they carry around a bunch of acid and they carry a bunch of base. Because if you get an acid spill, you put a bunch of base on it to neutralize it. You get a base spill, put a bunch of acid on it, and that'll neutralize it. But there's also chemical reactions that are important as acid-base reactions, and in general, it's a double replacement reaction. So the generic thing that happens is that you have an acid reacts with a base, and it doesn't just make water, but it makes some kind of salt. So I guess a really, really simple one to do would be hydrochloric acid, HCl, and then a base, sodium hydroxide, NaOH. If you react hydrochloric acid and sodium hydroxide, it's a double replacement reaction. This hydrogen and this hydroxide, they get together to make water, H2O, and then the chlorine and the sodium, they react together to make sodium chloride. So it turns out that if you can have super, super strong hydrochloric acid, and really concentrated sodium hydroxide, those two chemicals on their own are highly corrosive, highly reactive, somewhat dangerous chemicals, hydrochloric acid and sodium hydroxide. But if you mix them together in equal proportions, you just get salt water, just water with salt in it. Sodium chloride is regular plain old table salt. This could have a really low pH, maybe like the hydrochloric acid could have a pH of 1. The base sodium hydroxide could have a pH of 13. And this solution just has a pH of 7. So acids and bases commonly react together in these double replacement reactions. And generically, you get water and a salt. You actually wrote these reactions when we did double replacement reactions, but you didn't necessarily know that there was a specific kind of double replacement reaction called a neutralization reaction. You just kind of knew to write hydrochloric acid with its formula is how we write formulas for acids. And then you looked at sodium and hydroxide on the ion chart and periodic table, wrote that formula, and then you figured out it was like that. So the thing about water is there's another way to write water, and that's that if you have hydrogen and the hydroxide anion, how you would normally write a formula for a compound where it's a cation like hydrogen and anion like hydroxide would be to write the formula as HOH. Kind of the same as whenever you write sodium, Na plus and Cl minus, you just put them together like NaCl. So HOH is also kind of an acceptable equation for water. And when you think of water as an ionic compound, which is hydrogen and hydroxide together, or of water forming from two ions in a way like the same way any ionic compound forms, you can write it as HOH, but we don't really write it as H2OH. We write it as H2O. But H2O looks more like a molecular formula, and that's because water truly is a molecule and not as an ionic compound. So that's how when you put H and OH together, you end up with H2O. You write H2O instead of writing HOH. But that's not a completely unacceptable way to write the formula for water. Okay. Oh, yeah, I wrote it out, but in order for the neutralization reaction to take place, you would have to have the same quantity of hydrochloric acid as sodium hydroxide. There are no coefficients in front of the chemicals because, it's understood that there's a 1 here and a 1 here and a 1 here and a 1 here. We don't write the ones if there's one of each, but in some chemical reactions that are neutralizations, these quantities are not one-to-one ratios. Like if the acid has like 2 hydrogens or 3 hydrogens, like maybe in the case of sulfuric acid where it's H2SO4, or phosphoric acid which is H3PO4, then you would need a different coefficient in front to balance the reaction. And those coefficients in front of the reaction also tell you the relative quantities of each of the reactants that you need in order to completely make the neutralization happen. So if the ratio of hydrochloric acid to sodium hydroxide is 1-to-1, then you'll get complete neutralization and the pH will end up to be 7. But if there's more hydrochloric acid than sodium hydroxide, you treat it just like you would treat any excess reactant or limiting reactant problem. And if HCl is in excess, then the final solution will be acidic. If the sodium hydroxide is in excess, the final solution will be basic. But what we're trying to work toward is end up totally neutralizing stuff. So in one way, I don't know. I mean, hopefully you know, but your stomach is full of acid. It's hydrochloric acid. It's actually quite strong. It's very strong. You might know that hydrochloric acid can react with bone and teeth. So like it's gross, but if you vomit, you're throwing up hydrochloric acid and it passes by your teeth and it can do damage to your teeth even in a relatively short period of time. So if you have too much acid in your stomach, or if you have acid reflux, which people call heartburn, because you have the acid in your stomach is refluxing or regurgitating up into your esophagus and it causes pain. you can neutralize that acid with a base. And it turns out that um, antacid tablets like Tums or Rolaids, they have usually calcium carbonate or calcium hydroxide in them, which actually increases your calcium intake, which is good for strong teeth and bones. But antacids, the term antacid, these are called antacids, is ant means against or opposite of an acid. So really, an antacid is actually just a base. You're taking something that's basic, and as a result of having the like stomach acid and an antacid tablet, you end up making just salt and water, and it's actually going to be calcium chloride and water, which is totally safe. It's just in your stomach. So that's another common thing that you might do. If you don't have antacid tablets, you don't have Tums or something like that, any base will do, but don't drink like drain cleaner. That's stupid. But baking soda is a base, and it's kind of disgusting and weird, but you could take like a teaspoon of baking soda, put it into water, kind of swirl it around. It won't make a good solution. It's kind of chalky, and then just kind of like drink a little bit of baking soda and water, and the baking soda will react with the acid in your stomach and act as an antacid the same way as an antacid tablet does. So, except antacid tablets are manufactured with a particular quantity of base, and then there's dosing recommendations on the bottle. So you might know, like, oh, if you get a little heartburn, if you take one, you're good. Some people might take two or three at a time. You can't really OD on it. Antacids aren't like a gateway drug. It's like, yo, man, I took 8 of them. It was crazy. It's not like that. If anything, what happens is if your if your stomach acid drops too far, then your body recognizes that the acidity is too low, and then you have a natural response to vomit. Uh, I don't know if you know like the milk challenge where people will try to drink like a whole gallon of milk or a half gallon of milk. But milk is a base, and if you drink a whole lot of milk, it neutralizes the acid in your stomach, and your body's like the acid level dropped too far, and your body tries to pump more acid in, and the acidity won't recover. So your body just says, all right, I'll just start over from scratch. And then you just involuntarily throw up. And then your body's like, okay, now we can start over again. Starts filling your stomach up with acid. That's why the milk challenge is a thing that, you know, people can't do. You know about that? It's a dumb thing to do. It's also kind of like a waste of milk. I've never done it. So if you eat too much stuff or ingest too much stuff that's a base, that's a natural response. All right, so the plan is you need to have equal amounts of hydrogen and hydroxide. If you have equal amounts of hydrogen and hydroxide ions, then when the reaction takes place, all the hydrogen reacts with all the hydroxide, and you get an amount of water with no hydrogens or hydroxides left over. But if you have like, I'll do this by size. What if you have a whole bunch of hydrogen? Like you got a massive quantity of hydrogen ions, like a whole lot of hydrogen ions, like a big amount. And you react that with a small amount of hydroxide, like a little bit of hydroxide ions. As a result of the reaction, you're going to get some water, some quantity of water that forms as some amount of this hydroxide reacts with some amount of the hydrogen, but then you're still left with hydrogen ions left over if these boxes represent the relative quantities. Or on the other hand, if you have a little bit of hydrogen ion and a whole bunch of hydroxide, then when this reaction takes place, this hydrogen will react with some of the hydroxide and make some water, but you're going to have some hydroxide left over. And the deal is, if you've got excess hydrogen as a reactant as compared to the hydroxide, then you make water, but you have excess hydrogen. And this pH will be less than 7 because the final solution has some extra hydrogen ions. On the other hand, if you have more hydroxides than hydrogens, then the hydrogen will react with some of the hydroxide, leaving you some hydroxides to be left over, and the pH will be less than 7 or greater than 7. So you can also tell if you have an acid-base reaction whether the reaction is finished, and if you had excess or uh, like a limiting reactant based upon what the final pH is. Okay, so here's an example. We're going to figure out, based upon the quantities and molarities of different reactants, if you end up with a complete neutralization or if the solution ends up to be acid or base. This, in a way, is like an accumulation of all the things we've done in this course in a lot of ways. Because these are chemical reactions, it's useful to write the chemical equation rate out. We're going to take 50 milliliters of 1 molar sodium hydroxide. So sodium hydroxide is a reactant. We're going to mix it or react it with 25 milliliters of 1 molar HCl. So sodium hydroxide plus HCl, or to use this as an example, it's going to make water, H2O, plus NaCl. And the deal is that this equation is already balanced. There's 1 sodium hydroxide and 1 HCl. So if the quantity of sodium hydroxide and the quantity of HCl, the molar quantity, are the same, then it will be a complete neutralization. This is a volume, 50 milliliters of 1 molar HCl. The formula for molarity is the number of moles of the solute divided by the volume of solution. So that means that the number of moles is equal to the molarity times the volume. If I take the molarity, 1 molar, multiply it by the volume. Now, this is in milliliters, 50 milliliters. So you should convert from milliliters into liters, because molarity is the same as moles of solute per liter of solution. 50 milliliters every 1,000 milliliters is the same as a liter. So that's 0.05 liters. So if you multiply the molarity times the volume in liters, 0.05 liters, it's 0.05 mole. I know that I've got 0.05 mole of sodium hydroxide. And then we also have some hydrochloric acid. The number of moles is equal to the molarity times the volume. So if it's 1 molar and I have a volume of 25 milliliters, that's 0.025 liters. It's 0.025 moles. So I have 0.025 moles of hydrochloric acid, but I had 0.05 moles of sodium hydroxide. There's more sodium hydroxide than there is hydrochloric acid. That's the way the math works out. The reason why I showed you the math here, because you can also figure this problem out without having to do a whole bunch of math. It looks like we have the same concentration of the two solutions, 1 molar and 1 molar, but there's twice the volume of sodium hydroxide as there is hydrochloric acid. So it seems like there's a greater amount of sodium hydroxide than there was hydrochloric acid. In this problem, you don't really have to figure out the number of moles of each, but if the reaction is balanced so that the coefficients in front of the chemicals are not all ones, then it's not apparently obvious how the problem comes out to be. I'll show you an example of that. So the deal is, all of this hydrochloric acid will react, but not all the sodium hydroxide will react. The sodium hydroxide is the excess reactant, and the hydrochloric acid, that's the limiting reactant. And as a result, because sodium hydroxide is in excess, not only do we get water and sodium hydroxide or sodium chloride, there's going to be excess hydroxide ions. There's actually excess hydrogen or sodium ions and excess hydroxide ions in solution. So the pH is going to be greater than 7 because we have an excess amount of hydroxide ions. For any other kind of limiting reactant problem we did, like a single replacement or double replacement reactions, if none of the reactants are acids or bases, then you just have excess reactant just left over kind of chilling, and it doesn't affect the final solution in any kind of way. But if one of the reactants is an acid or a base, and it's an excess or limiting reactant, then the final solution isn't necessarily neutral. It could be um, acidic with a pH greater than 7, or it could be basic or basic with a pH of greater than 7, like this one, or it could be acidic with a pH of less than 7. So the ion that's in excess, that's left over, is hydroxide. There is also excess sodium, but sodium ions, they don't affect the pH of the solution. They're just excess sodium ions in solution. They're just sodium ions floating around along with hydroxide ions. All right, so now, what if the reaction doesn't have coefficients all of 1? So here I'm going to take sodium hydroxide again, NaOH, and react it with H2SO4. That's sulfuric acid, H2SO4. That's going to make water, H2O, and then the other ions are sodium and sulfate. Sodium has a charge of 1, and sulfate has a charge of 2 minus. So you make Na2SO4. And that equation is not balanced. You need to put a 2 in front of the sodium hydroxide. And a 2 in front of the sodium hydroxide balances the number of sodiums. And then you got to check the hydrogens and oxygens. And here's a shortcut to figuring out the balance for hydrogens and oxygens when you have an acid-base reaction. It looks like there's 2 oxygens here, and then there's 4 more oxygens on the right-hand side, or on the sulfuric acid. So that's a total of 6 oxygens. And then on the right-hand side of the reaction, there's 4 oxygens here and only 1 there. So it looks like you might put a 2 in front of here. But here's a smarter thing to do. Although you write water as H2O, if you think about it as HOH, then really what you want to do is you can also think about balancing the hydrogens, which are here with this hydrogen, and then think about balancing this hydroxide with this hydroxide. And you can see that because there was a 2 in front of the sodium hydroxide, there's 2 hydroxides, and because there's a 2 after this hydrogens, there's 2 hydrogens. So when you put a 2 in front of the water, that gets you 2 of the hydrogens by itself, and then 2 of the hydroxides. That's another conceptual way to help you balance it. And because it can be tricky with some acid-base reactions where you'll have, especially with oxyacids, where you have oxygen both in the water and oxygen in the anion. But another trick here too is because the sulfate, there's 1 sulfate, over here there's 1 sulfate. So don't try to balance the oxygens, try to balance the groups of ions. Balance the hydroxides with these hydroxides, balance this hydrogen with this hydrogen, and then balance the sulfates so that you've got equal amounts of each of those. Anyway, that's like a little side trick. Okay, now I got 50 milliliters of 1 molar sodium hydroxide. You can figure out how many moles of sodium hydroxide that is. So the number of moles is equal to the molarity times the volume. If I take 1 molar times 50 milliliters, it's the same math as like in the last one. It's 0.05 moles. And then 25 milliliters of 1 molar sulfuric acid, it's the same as the last one. 1 molar, 0.025 liters. It's 0.025 molar. But in this reaction, for every 2 sodium hydroxides, you only need 1 H2SO4. And it turns out you have twice as much sodium hydroxide as you have H2SO4. So if you remember what we did with figuring out limiting and excess reactants, we took the quantities of each of the reactants and figured out how much product you could make with the quantities of each of the quantities of the reactant using mole ratios. So there's two ways to go about this. One way, you can just use a little bit of logic and say, all right, I have twice as much sodium hydroxide as I have sulfuric acid. And in the reaction, it says that I need twice as much sodium hydroxide as I need sulfuric acid. So I've perfectly satisfied that condition, and it looks like it could be neutral. But a way to make sure that the math works out, and sometimes the math isn't easy, like usually the math isn't easy, like in this one. If you take the amount of each reactant, like 0.05, hold on, I gotta quit a program. I got too much stuff going on here. This is all being slow. Where'd my cursor go? Here it goes. Let's see what else is open. Oh, Excel. All right, that's better. Okay, so you can take this amount of sodium hydroxide, like 0.05 mole of sodium hydroxide, and use the mole ratio in the equation. So I've got, in the equation, it says for every 2 sodium hydroxide, and it really doesn't make a difference which of the products you pick. I'll just pick the water. You get 2 moles of water. So as a result, this 0.05 times 2 divided by 2 is 0.05 mole of water. And you can do the same thing with sodium hydroxide, or the sodium hydroxide over here. So we had 0.025 mole of, or I'm sorry, this is sulfuric acid, H2SO4. And in the equation, for every 1 H2SO4, you get 2 moles of water. So that is also 0.05 mole of water. In other words, the quantity, the amount of sodium hydroxide, the molar quantity of sodium hydroxide is enough to make 0.05 moles of water, and the molar quantity of sulfuric acid is also the right amount to make 0.050 moles of water. And as a result, the quantities of each of the reactants makes exactly the same amount of each of the two products, and this reaction is a complete neutralization. We end up with a pH of 7. So there's no excess hydroxide and there's no excess hydrogen, because each of those quantities of sodium hydroxide and sulfuric acid make exactly the same amount of water. It ends up to be exactly pH of 7. So a lot of times the quantities of reactants aren't nice and even numbers. The concentrations aren't always the same. The ratios of the volumes aren't the same as the ratios in the equation. You could have all kinds of different issues. So this third one, I've got 30 milliliters of 0.5 molar sodium hydroxide and 20 milliliters of 0.4 molar sulfuric acid. This volume is 50% greater than that volume. This molarity is 25% greater than this molarity. And when the reaction takes place, the mole ratio of the sodium and the sulfuric acid are not 1-to-1. So it's definitely not easy to know just by looking at the quantities how this one turns out. But all the time, you can write the equation for the reaction, sodium hydroxide and sulfuric acid. It's the same one as the previous one, makes sodium sulfate. I'll write the water first because I had the water first in the other one. H2O plus Na2SO4. You got to put a 2 in front of the sodium hydroxide and a 2 in front of the water to balance the equation. So the equation's balanced, same as the previous one. I'm going to figure out what quantity, molar quantity of sodium hydroxide is in this solution. The molarity, or the number of moles, is equal to the molarity times the volume. So I'll take 0.5 molar, and 30 milliliters is 0.030 liters. So that comes out to be 0.015 moles. We have 0.015 moles of sodium hydroxide. And this 20 milliliters of 0.4 molar sulfuric acid, the number of moles there is 0.4 molar times 0.020 liters. So that's 0.008 moles. So now it looks like you need twice as much sodium hydroxide as sulfuric acid in order to make the neutralization complete. When you compare these quantities, this was the number of moles of sodium hydroxide, and that's the number of moles of H2SO4. The equation says that you need to have twice as much sodium hydroxide as sulfuric acid. So if you double this amount, 0.008, that would have to be 0.016. And we don't have 0.016 moles of sodium hydroxide. We have only 0.015. So there's less sodium hydroxide than what you would need in order to neutralize all the H2SO4. That's a way to think about it conceptually, but mathematically, the way to deal with it is to take this amount of sodium hydroxide, 0.015 moles sodium hydroxide, and use the mole ratio in the equation. For every 2 sodium hydroxide, I get 2 moles of water. So this ratio will then tell you how much water you make with the quantity of sodium hydroxide you've got, 0.015 moles. And the same thing's true with the sulfuric acid. I have 0.008 moles of H2SO4. This mole ratio is for every 1 H2SO4, I get 2 moles of water. And that's 0.016 mole of water. So in the end, you have enough sodium hydroxide to make 0.015 moles of water, but you have enough sulfuric acid to make 0.016 mole of water. So there is a greater quantity of sulfuric acid available to make water than there is sodium hydroxide. This is the greater quantity. So I guess you could say the number of moles of sulfuric acid can make more water than the number of moles of NaOH. And as a result, that means that H2SO4 must have been the excess reactant. This is the excess reactant. And the sodium hydroxide is the limiting reactant. All the hydroxides are all going to get used up and change into water. But because the sulfuric acid is in excess, there's going to be some more hydrogens in that solution than the number of hydroxides. And so then we have, I guess you could say, you don't really write it in the equation, but we have some excess hydrogens, and that makes the pH less than 7. So if you were to take 30 milliliters of half molar sodium hydroxide, mix it with 20 milliliters of 0.4 molar sulfuric acid, a whole lot of it will neutralize, make sodium sulfate and water, but there will be excess hydrogen and sulfate ions in solution. And because there's excess hydrogen ions in solution, it's an acid, and the pH will be less than 7. If the reaction takes place so there's no limiting or excess reactant, then the pH will be exactly 7. You could test it with universal indicator. You could test it with litmus paper. So in the case of this reaction, if you were to put red and blue litmus paper in the final solution, the red will stay red and the blue will change red. if in the previous one, like number 2, because this one comes out to be a pH 7, this is why you can't just have one color of litmus paper. You might say, oh, I'm going to put red litmus paper in and it stays red. That means it's an acid. Not true, because when you put blue in a neutral solution, it'll also stay blue. So the only time something is truly an acid is if you actually have both of them change red, or in the case of example 1, where the pH is greater than 7, the blue paper will stay blue and the red paper will change to be blue. All right, so there's this other page. Let's see, show desktop. The in the end of the folder for the week, there's a set of problems here. It says, first write the chemical equation between HBr and LiOH. That's hydrobromic acid and lithium hydroxide. And in each of these cases, you want to consider, well, what if we mix different quantities of hydrochloric acid and sodium hydroxide, hydrobromic acid, sodium hydroxide, hydrochloric acid, lithium hydroxide. As a result of mixing those quantities of the two acids and bases, do you end up with a solution that has a pH of greater than 7, less than 7, or equal to 7? And same thing down here. So you write the balance equation for calcium hydroxide, hydrochloric acid. And if you mix that quantity of calcium hydroxide with this quantity of hydrochloric acid, does the final solution come out with a pH of 7, where it's completely neutralized, there's no excess reactant? Or does it come out with a pH less than 7 because there's excess hydrochloric acid? Or does it come out to be a pH greater than 7 because there's excess of the calcium hydroxide? So you can try those. You can do them now or do them whenever. We'll go over those 4 at the beginning of class tomorrow as like a good practice. Let's see more.